All right. Hello, everyone. As I sent my announcement, I caught the plague of some sort, so I'll keep my distance from y'all and all that. I mean, I'm nature of lecture class. I'm already so far away from y'all. But yeah, if you're wondering why my voice sounds like I've been smoking for the last 4 days, that's why. As long as it holds out for this class, I'll definitely recover by Thursday, right? That's all you think. All right, so this one's good. Did you hear about the mathematician who's afraid of negative numbers? He'll stop at nothing to avoid them. Stop at 0 so you don't go to negative. Yeah, the nice thing with these is I get the joy of getting to explain them too. That's half the fun in telling wordplay jokes. But anywho. All right. Last class we finished center mass, did some equations, did some things. Your labs, you get some nice practice with it this week. And then we started fluids. And fluids has a big laundry list of things I need to teach you all. And so the reality with fluids is, like everything in this class, you all really need to go through the problems because like every 2 problems is a different concept, a different skill that's being used. There's so many concepts and equations in fluids, and I say that not as like a bad, in my opinion, it makes it more straightforward because when you realize what type it is, it's like you just choose that equation and you do the things. But yeah, you're not going to be familiar with them unless you've done them. So last class we started talking about density. We'll do, and every single one of these, I'm going to do an example of them in this PowerPoint slide. Like I was telling you all, you need to do these to make sure you've done one of each. Let's just count how many I'm going to do with you all. There's 1, 2, 3, 4, 5, 6, 7, 8. I'm literally going to do 8 of them because I have to show you all how to do them, and the best way to show you how to do them is to do them. So there is so many practice examples in this PowerPoint because there's so many things you have to practice. I wouldn't say any of them are necessarily tricky, but people may differ on that. Whatever, we'll see. We'll see how this fluid stuff goes. I think it's nice and straight. Like I like it a lot. I think it's super interesting. So we start with density. Density is what you want it to be. It's mass over volume. One of the things that's a little unpleasant about fluids is all the different units. So this is going to be a trend. You do not need to have these memorized, these unit conversions. I will provide them to you on the test. So for specifically like this one down here, I will provide that to you. 1 liter is 0.001 meters cubed. I will provide that to you. If you all need the density of a fluid in a problem, I will also give that to you. I don't expect you to have memorized the densities of various things. Pretty much the one that's always going to come up is the density of water, and I'll give that to you in a problem. In general, we're going to want to use this one. The density of water is 1,000 kilograms per meter cubed because it's in the nice space units and all that good stuff. All right, cool. So we did a problem. We found the mass of water. Yay. So this is our first problem here, and we got a 2.5 kilogram steel gas can. It can hold 20 liters of gas from full. What's the average density of the full gas can? Taking into account the volume occupied by the steel as well as the gas. And then I give you the density of gas is 0.68 times 10 to the 3. Density of steel is 7.8 times 10 to the 3. Average density means the density of all of it together. And this is, in the real world, when you're working with the density, it's very rare for you to have an object that's just one thing. It's very rare for you to have an object that's like homogeneous. So, for example, your human body, if you all found the density of your human body, that's made up of so many things: bones, muscles, fat, other things. And when you get the density of a human body, it's all of it together. So this problem is teaching us how to actually like calculate the density of an object if you kind of knew all the pieces. Most often in the real world, you would measure the density of an object and you'd actually work backwards. So an example of this is if you found the density of a human body, you could actually work backwards to find like the amount of fat in someone's body. Like that's one way that they determine body fat percentage is they find the density of a human body and then they say, okay, the average human has this much muscle, this much bone, and then whatever's left over is fat, basically. And they do that. So, great. We're going to do this similar practice, the thing I've been mentioning to you all. We're actually going to start with solving for. We are solving for average density. It's just the density of everything together. Like the word average here, we're not actually averaging anything. We're just getting the density of everything together. Whatever. So we have the mass of my steel. That's 2.5 kilograms. We have the volume of my gas, and that's going to be 20 liters. We are immediately going to convert that to meters cubed. Like that's generally something you just kind of want to do. So that's going to be 20 times 0.001. That's the unit conversion. So it ends up being 0.02 meters cubed. And then, yeah, we got the density of gas is 0.68 E3. Again, this is in meters cubed. That's where we did the unit conversion. And the density of steel is 7.8 E3. Yay. All right, and what you all think of it, how the heck are you going to find the density of everything together? See if you can think of the strategy here before I give you the magic punchline. Oh, I'll even give you a hint. There's literally only a single equation for density. But think about how you would use that. And the word average here might be kind of misleading. Again, you're not actually going to take two numbers, add them together, and divide by 2. Don't do that. That's not going to work. That would mean you're assuming you have equal amounts of each, which is not going to be true. And maybe a better way to do this would be like momentum total, like the momentum of the entire thing. Again, that might make you think, oh, I'm going to take the two densities and add them together. That's not going to be the case. But if we think about like momentum total, not momentum, density total, it kind of gives us a sense of what we're going to do. We're going to get the mass of the steel plus the mass of the gas and divide it by the volume of the gas and the volume of the steel together. Get all your mass, get all your volume. If you do mass divided by volume, ta-da, you get density. So that's the key here. If you ever want to get the density of anything, get the mass of the thing, get the volume of the thing, divide it together. If you have a system with many things, just add up all their masses, add up all their volumes. And this is how you can calculate the density of any object, even if it's made up of a bunch of different materials and things like that. Just get the mass of each individual item, get the volume of all the items, and yay. So, when you look at this, though, you hopefully realize I don't have the mass of the gas. I don't have the volume of the steel. So then, how are you going to get those? Well, how am I going to get the mass of the gas? Well, density equals mass over volume. I can rearrange that so that mass equals density times volume. So if I want the mass of the steel, I just multiply the density of steel times volume of steel. And that's we have those things. Density of steel is 7.8 E3. The volume of the steel, oh, no, sorry, we don't know that. We have the mass, oh, we're doing the gas. I just put the wrong things there. We want the mass of the gas. That's the one we don't have. So we're going to take the density of the gas, which is 0.68 E3. We have the volume of the gas, that's 0.02. And so the mass of the gas is something. It's really not going to, well, no, it's actually going to be a lot. Let's say this one's actually quite big. 13.6 kilograms. You got 20 liters of gas, it's got a decent amount of mass. Yay. All right, if you want to get the, what color? We'll do the other blue. If you want the volume of the steel, so density equals mass over volume. Volume, I'm actually going to write out this whole thing. Volume times density is going to equal mass. Therefore, volume of the steel is going to equal density, mass of the steel divided by density. Just did some algebra, move things around. So volume of steel equals 2.5 divided by 7.8 E3. Divide those and you get a number. 0.000321 meters cubed. Yeah, the steel doesn't take up that much space. It's not about how much space the gas can takes up. It's about how much literally the steel walls, how much space do the steel walls take up, is what we found. And then we just take all this and we chuck it, and then we chuck it into the equation and we get our answer. So this entire problem is just doing density. Density equals mass over volume. Density equals mass over volume. And then you just put it all together. So great. If we want the overall actual density, then we're going to take the mass of the steel, which is 2.5, plus the mass of the gas, 13.6, over the volume of the steel, 0.000321. Plus the volume of the gas, which is 0.02. We plug that whole thing in our calculator, and we'll get the density of the entire object. You just got to be careful with your parentheses and all that stuff when doing this. And you get 792.284 kilograms per meter cubed. Yay! It's a number that's in between the two values. It's smaller than the density of steel, but it's bigger than the density of gas. It's somewhere in between them based upon the amounts I had and all that stuff. Okay. Something I was just reminded of in my head that I wanted to mention to you all. So one, I'm making your all's exam. I think I made a first draft of it. I need to go through and double check some stuff. My goal will also be to make a practice exam based upon previous quizzes and the test I just made and the problem sets or whatever. Basically, my goal is to make a practice exam without making a whole nother separate whatever. I hopefully will have that done by Friday. It'll probably be like 20 multiple choice questions. Probably no free response because you all have a whole bank of problem sets that are like basically free response questions. So I'll give you all a practice like multiple choice exam. For the exam for the free response, so remember the emphasis of this exam is energy and momentum. There is fluids as well, so there'll probably be, out of your 18 multiple choice, probably 6 will be fluids. And the other 12, 6 of them will be energy, 6 of them will be momentum, something like that. But the free response, no matter which free response you pick, one part of it will be energy, the other part will be momentum. So either part A is energy, part B is momentum, or part A is momentum and part B is energy. None of the free responses will have fluids. Those will all be multiple choice. So anyway, what I want to mention to you all, because I kept forgetting to do this, There's two problems in the problem set that you don't need to bother with when it comes to energy, because I think they're not worth it. If you already did them, awesome. But I think they add too much. They result in more confusion than they're worth. It's 12 and 13 in energy. Number 12 and number 13 in energy, you do not need to worry about solving these ones. You can if you want to, but they honestly result in more confusion than they're worth. If you already did them, good on you. It's still useful, but they have some nuance to them that just doesn't add much. There were problems I added this semester to the problem set. I will not have them in the future problem sets. But such is the nature of improving education and all that. But I wanted to mention it to you all in case you hadn't done them yet. Spare you some suffering. If you did, nice work. All right. Cool. Fluids. Great. Okay. Density. We're going to learn lots of interesting. Density is going to come up so much in fluids. The only reason you're going to use mass in a problem is to find density, and then you'll use density to do other stuff. Everything to do with fluids, we care about the density instead. And you'll see why as we solve problems. But one of the cool things with this, the one that you're probably familiar with, is density determines whether or not stuff floats. So if the density is less than water, it floats. If it's greater than water, it sinks. Like, that's just rule of thumb, super easy. We're going to kind of sort of learn why that is. Is this number bigger or smaller than the density of water? What say y'all? Bigger or smaller? Take your vote. What's the density of water? Let's start there. It's 1 gram per milliliter. We got to convert it to kilograms to meter cubed. The density of water is 1,000 kilograms per meter cubed. If you have a meter by a meter by a meter of water, it will have a mass of 1,000 kilograms. It's a lot of water. This is smaller than that. This will float. One of the fun facts we're going to learn is that if you divide this by the density of water, you'll get the percentage that'll be below the water line. So if you divide this by 1,000, you're going to get 0.79. That's the percentage that'll be below water. 79% of this object, if you stuck this thing in water, 79% of it would be below the water line. That's one application of this. Again, there's going to be many, many, many applications of density, but it's one of like the easiest ones to kind of convince. All right. The next really important thing is pressure. Pressure is something you've heard about before. But yeah, we're going to learn how it applies to fluids. Pressure is not the same thing as force. Pressure is force over area. So we'll see some examples of this. The reason we talk about pressure is, like, imagine you all like filled a water balloon and I said, how much force is acting on the walls of this water balloon? Like, how much is being pushed outwards on it? You would take the pressure of the fluid inside and you multiply it by the area inside it, and that would give you the force of it. And the reason that's really important, we're going to learn that pressure inside a fluid is the same everywhere in the fluid. Every single place in a fluid, assuming you're at the same height, pressure is the same. It gets carried throughout it. And this has all sorts of cool applications to it, but whatever. We'll get to that. Force per area. That's the definition of pressure. My gosh, there's so many units for pressure. We're only going to use 2 in this class, but there's like 5 I could think of. We're going to use metric, which is pascals. It's a Newton per meter squared. Newtons, you've heard of newtons. Meter squared, you've heard of meters squared. Where do these come from? The unit for force is newtons. The unit for area is meters squared. You divide those and ta-da, and that's a Pascal. Why is it called Pascal? It's named after a guy named Pascal. So PA stands for Pascal. I kind of took that for granted that people might know what that meant. Could have done a better job there. Pascal is what that PA stands for. Now, in the medical field, you're actually more commonly going to work with millimeters of mercury, which is kind of a really funky unit because it's based on how it's measured. where you have like this device where there's a fluid and mercury, and as the pressure goes up, the mercury rises up a tube and all that jazz. All you need to know is that 1 millimeter of mercury equals 133 pascals. That'll be given on a test. Like if you need that, I'll give you that unit conversion. You don't need to have that memorized, but that's going to come up in problems. And like I mentioned down here, a large pressure does not necessarily mean a large force. You all can see that from the equation. Sure, if force is big, you get a big pressure. But there's another way you can get a big pressure if area is small. If you make the area really, really small, you get a really, really large pressure. Great. Why does pressure matter? That's going to show up in future slides. Pressure is just going to come up again and again and again and again and again. It's so relevant. It's so important for fluids. And we're going to see that as we do stuff with it. So for now, just trust me, it's important. All right. And now we practice. The aqueous humor, which I've been told is the fluid in someone's eye, exerts a force of 0.3 newtons on the 1.10 centimeter squared area of the cornea. What pressure is this in millimeters of Hg? And is this value within the normal range of pressures in the eye? Part B is not something I'm going to ask on a test. That's just fun facts. If you were doing this in the problem set, you would just Google what the normal pressures in an eye are. So think about it. See if y'all could solve it. See if you make the right decisions and all that good stuff. And feel free to chat with each other and make sure you're both doing it the same way. All that good stuff. All the fluids problems, there's basically only one right way to do it. All right, so we're going to start with step 2. We're solving for pressure. We are given force, 0.3 newtons, and we're given the area. And this is where if you made a mistake, this is where the mistake's going to have happened. This area is 0.00011 meters squared. Now, I'm going to show, I did that unit conversion really quick. And if you had said that if you did the unit conversion and you got it as 0.011, I'm going to show you all why you have to do it twice. When you're converting from centimeters squared to meters squared, I'm not converting centimeters once, I'm converting it twice because it's squared. So let's just kind of write that out up here. 1.1 centimeters squared. I want to convert that to meters. The second you all saw centimeters, that's like a red flag that you need to convert to meters. Like that's something that we just have to do. So we ask ourselves, great, I want to convert to meters. So we do this little handy thing. I put centimeters on the bottom so it cancels. We know that there's 100 centimeters in a meter. If I did this as is, I've only canceled one of my centimeters. It's centimeters squared. If you want to cancel both of the centimeters, if you want to convert both of them, because it's squared, you need to do this twice. And when you do this twice, the first time you move the decimal place 2 places, you do it again and you move it another 2 places. Overall, you need to move it 4 places. So when you're converting areas, you have to do the unit conversion twice. If you were doing a volume, you'd have to do the unit conversion 3 times because it's centimeters cubed or whatever it might be. So yeah, this would come out to 0.00011. Another way for me to prove this to you all is imagine that we did 1 centimeter times 1 centimeter. That equals 1 centimeter squared. Hopefully we're cool with that. If I wanted to convert this to meters squared, I would convert both of these. I did a unit conversion twice. And so we can see here, when you do the unit conversion twice, you get something that's way more different. You get 0.0001. So this is just to show you all, again, it's a subtle thing. If you understand it, awesome. If not, this is one of those things you just got to be careful of. Great. Pressure equals force over area. Step 4. Pressure is going to equal 0.3 divided by 0.00011. Now the unit that this is going to spit out is not millimeters of mercury. If you all have any context for medical stuff, if you all measure the pressure in someone's body as 2,700 millimeters of mercury, it's just not possible. Your body can't contain that. Like that pressure, that many millimeters of mercury is like insane high pressure. So great, we got to convert it. How do you convert it? Remember, y'all, 1 millimeter of Hg is 133 pascals. Just divide it by 133 and you're good to go. That's all you got to do. So if I want the pressure in millimeters Hg, I take my original pressure and I divide it by 133. And that spits out that 20.5. And if you Google it or ask ChatGPT, they say something like between 18 and 21 is good. And yay, this person's eye is fine. This is something people test. They test the pressure in people's eyes. How do they do it? I actually don't know. I haven't looked it up. But they definitely care. So there you go. Nice, simple problem about pressure. Testing, the equation is so easy. So this problem is really just testing, can you do the unit conversions? That's basically the main thing. All right, 2 things down. We've talked about density. We've talked about pressure. Now we're going to put them together and kind of, sort of. You'll see what I mean. I got to open Top Hat. So I have 50 kilograms of water inside a large container. What is the magnitude of the force pushing down on the bottom of the container? Don't overthink this. In fact, I'll give you all a hint. Why is the water pushing down on the bottom of the container? Gravity, great. Go from there. That's all you got to think through here. If I say what's the force pushing down? The next question is it pushing down? If so, why? And then you go from there. This question and the one following it are to help us learn something new. It's putting stuff together. All right, we'll go like 10 more seconds. All right, in 5, 4, 3, 2, 1. All right, so again, I kind of gave away a decent amount of this. Why is it pushing down? Because of gravity. Great. What's going to be that force due to gravity? It's just m times g. It's just 50 times 9.8. It says magnitude, so we take the absolute value. And yeah, it's 490 newtons. That's the only answer that was possibly reasonable. Nothing has changed. Just because we're talking about fluids doesn't mean gravity doesn't stop existing. Okay, so what? We got another question to ask, and then we'll be able to put it all together. So reminder to you all, 9.8, that's going to be meters per second. That's the acceleration due to gravity. You always got to multiply it by mass. M times G, M times G. F equals MA. And if gravity is the acceleration you care about, all that stuff. So, great. All right. Which equation relates area, height, and volume? I'm going to take these two slides and we're going to slap them together to derive a new equation. That's the reason we're doing this. And one little trick you can do here is play around with the units and see what units work out correctly. Which of these equations will make my units work out the way I want them to. All right, we'll go like 10 more seconds. If you're not sure, go with your guide. All right, in 5, 4, 3, 2, 1. All right, there's two ways we're going to figure out the answer here. One, we're just going to look at the units. The unit for area is meters squared. The unit for height is meters. The unit for volume is meter cubed. So if you just play around with these equations, the units should work out. For example, this first one, if I did meters squared divided by meters, that spits out meters. That's not volume. If I do the next one, meters divided by meters squared, that's meters to the negative 1. That's not volume. This one's going to be meters squared times meters. That's meters cubed. Yay! And the last one doesn't work because it's meters squared times meters squared equals meter to the 4th. Also not volume. So, bad, bad, bad. Great. That's one way to do it. The other way to figure this out is I give an example of a cylinder. Cylinder's really nice. If you wanted to find the volume of the cylinder, how would you do it? You'd find the area of a circle, and then you basically ask yourself, how many circles do I have? I have H circles. You can imagine like we're stacking these circles on top of each other all the way up to the top. So the area down here is pi r squared. H is H. So if you want the volume of a cylinder, it's actually really easy to derive if you know the area of a circle. It's pi r squared times H. You don't need to know that, but that's just another way to prove it. It's area times height. Great. Why does this all matter? All right, we're going to take the density equation and the pressure equation together, and we're going to do some stuff with them. So, first thing we're going to do, density equals mass over volume. Great. rearrange this. Mass equals density times volume. Still nothing crazy. Hopefully no one's surprised at this point. All right. Now what we're going to do is we're going to replace mass is going to equal density times area times H. Great. Cool. Just plugging in the things that we found. Okay. Now we're going to look at the pressure equation. Force over area. As you have a fluid, so as we just found, if you had a tank of water, at the bottom of the water is literally pushing down. Why? Because gravity's pulling it down. So hopefully we're cool with, at the bottom of some tank, there's a force due to gravity from the water. Awesome. So pressure is going to equal M times G over A. Great. Now we're just going to take this mass, and we're going to put it right there. So we do that, and we get that the pressure, the areas cancel. And if you want to find the pressure somewhere in a fluid, you just measure down how far you are, multiply it by the density of the fluid, multiply it by gravity, and that's the pressure. So if you're in some tank of water, some distance down, some distance h, you can find the density. This slide has it derived a little bit prettier, but it was all at once. I like to kind of work it out, but it's the exact same thing I just did. And then the next slide has it again. So I'll draw a picture of this. I say draw. I'll actually, they have cylinders in here. I should have included a visual. So if you have some container of water, whatever, there it is. And it's filled with some water. Let's just say it's filled up to here. Yay, it's filled with water. If you want to find the density, the pressure at this point, all you do is you measure this H, you plug it into the equation, and that gives you the pressure at that point. What's really interesting about this equation, you don't care how wide the container is. If this container was super, super thin like a straw, or super, super wide like the ocean, it doesn't affect it at all. So that's the weird thing about this equation. And why does the area not matter? Remember, y'all, it canceled. The pressure canceled. Or sorry, not the pressure, the area canceled. As you get deeper, the pressure increases. But if I took this picture and I made it really skinny, it's the exact same thing. The pressure is exactly the same. If I made this container massively wide, doesn't matter. So it's a really weird thing that happens that's pretty cool. Oh, and I forgot to add the link to the video. Yeah, so one of the interesting consequences of this is there's a limit to how long of a straw you can drink from, which sounds kind of stupid. But if you had a straw the size of like a 2-story or 3-story building, you can't actually drink water from it because the amount of pressure, like the reason a straw, and this is a complete aside, and I'll be very quick on this. The reason a straw works, something you probably haven't even thought about, you're just like, it works, you know? Sure. You probably never thought about how a straw works. The way a straw works is when you basically suck on a straw, you're pulling the air out of the top of the straw. You're kind of creating a vacuum at the top of the straw. Why does that matter? It turns out that the atmosphere is pushing down on this water. You don't realize this, but the atmosphere is pushing down on you right now. Why does it not matter? Because the atmosphere is also, you're breathing in air, and that air pushes outward, and it all cancels out. So normally when you don't suck on a straw, nothing happens because the atmosphere is pushing down on it everywhere. But when you remove this, the water, is going to start to go up. When you take away the air, there's a difference in pressure whenever it goes up. The problem is the atmosphere can only lift this water so high. And because of this equation, it doesn't depend upon how big the straw is or anything like that. At some point, it gets so high that you literally just can't lift it anymore. There's a limit to it. And there's a YouTube video, and I'll post it in the thing here. I had it in my other one, but I forgot to put it here. Oh, well. But great. Here's the question I do want you all to be able to answer. So this is an important question. This is an important concept when it comes to fluids. How does the pressure at the bottom of a 10-meter deep pool compared to the pressure at the bottom of a 12-meter tall straw? Both are filled with water. Is the pressure at the bottom of the pool bigger than the pressure of the straw? Is the pressure at the bottom of the pool less than the pressure of the straw? Is the pressure the same, or both pressures are zero? And, there's the equation. All right, we'll go like 10 more seconds. All right, in 5, 4, 3, 2, 1. So I mentioned this several times. The only thing that matters is H. If they're both filled with water, all you care about is their densities are the same. So if we have the pressure for the pool, that's going to be the density of water, 1,000 times 9.8 times 10. Boom. That'll spit out the pressure of the pool. Pressure of the straw is going to be 1,000 times 9.8 times 12. 12 is a bigger number than 10. So that one's going to be bigger. The straw is going to be bigger. And this is the weird thing with pressure that always throws people off. The pressure at the bottom of the straw will be larger than the pressure of the pool. You only care about how much fluid's above you. You don't care about the fluids on the side. And another way to kind of explain this, if you're inside a tank of water, what ends up happening, and this is kind of funky, the water on the sides is pushed, it's just the force of it's not really a reason for it to actually push you. The only reason there's a pressure here is because of gravity, and gravity's only down, and the only ones that's going to affect you is above you. Like these ones over here, they're not pushing down on you. Another way you could think about it is there's equal and opposite, the water on the left, water on the right, but that doesn't quite do it. Really, the best way to think about it, gravity's only down, so you don't care about the left-rights. Now, I will say, if you measured the force at the bottom of the pool, if y'all remember, pressure equals force times force divided by area. If you all rearrange this, the force at the bottom of the pool is going to be much larger. The force over the entire bottom of the pool. That's really important. This force is spread over the entire bottom. It's not focused at one point. The total force on the entire bottom of the pool is much larger than the total force at the bottom of the straw. That makes sense. Like, a pool's really heavy when it's filled with water. But the pressure is not dependent upon that. So, anyway. All right. So, medical application, because these are interesting. When you all measure someone's blood pressure, where do you measure their blood pressure at? It's on their arm. Why? It's the same height as the heart. When you're measuring the blood pressure in someone's arm, you're trying to measure the blood pressure at the heart. Why do you pick the arm? Because it's at the same height as the heart. If that person's arm was lifted in the air, it's not going to be the correct value. The pressure will be lower because it's at a higher point. There's less fluid above it. So, this problem says, suppose you measure a person's blood pressure by placing the cuff 0.5 meters below the heart. If you observed at the heart, if it was 120 over 80, which I don't like this notation, but I get why. This 120 over 80 is not 120 divided by 80. Mathematically, that's what this says. 120 over 80 says 120 divided by 80. That's not what it means. It means pressure, and you all know this. I'm sure most of you do. But for those IT majors that are like me, that don't do medical things, the 120 is the high, and then the 80 is the low. And then there's words for these that I forget that someone reminded me of this morning. Systolic and the other diastolic something. I don't know. It's based on when your heart beats, it makes a high, whatever. You all know this, I don't need to tell you. There are two different pressures. So our answer is going to have two different answers. We're going to calculate two different blood pressures. They're relevant because of medical stuff, which you all like. Anyway, so we're going to find what this blood pressure would be at someone's feet. 0.5 meters, somewhere in their leg or something. And I gave you the density of blood, because we're going to need that. So density of blood. Density of blood is a little bit more dense than water. Makes sense. It is water with a bunch of junk in it. So it's going to be more dense than water. All right, great. What are we solving for? You can kind of label this as you want. Ah, gosh, it's tricky for me to think about that. How would I write this? I want to find the pressure at 0.5 meters. I'm just going to write that. Now I want it the high, and I want the pressure at low. That notation to me makes sense. Put whatever notation to you makes sense. We want to find the pressure somewhere else for the high, and then somewhere the pressure else for the low. Now, how are we going to do this? I want you all to think about how you would do it. What's interesting in this problem is this problem only is true on Earth. Like, the numbers would be identical if you're in space, actually. It wouldn't matter where you measured it. But since we take our blood pressure measurements on Earth, it matters. All right, so the way I'm going to kind of write this, and this might look a little silly, I'm going to call it like the total. Your blood pressure is going to depend upon two things. One, it's just going to depend upon what the blood pressure is due to the heart, which is those numbers. But it's also going to depend upon the blood pressure due to gravity. Your heart is creating some pressure. We know those values. And then gravity is creating some pressure because there's literally a bunch of fluid above it, and that's going to push down. So the pressure is going to be the combination of the two. Now, I did make this plus. That's because I know the pressure is going to go up if you go down. Because I got a really good question here in my previous class. They're like, oh, do I make this this 0.5? Do I make it positive or negative? And basically the way to think about this is it increasing your pressure or decreasing it? That's really, there is no such thing as a negative pressure. That's something that's also important. Pressure is always positive. So anytime we do these problems, we're going 0.5 meters down. Your pressure is going to go up. So we're going to add it. So this pressure due to gravity, that's going to be the whole rho GH thing. So long story short, I think this is just easier to kind of write out. If I want to find the blood pressure, the high one, I'm going to take that one. Well, and we got to be careful here, actually. Let me calculate the pressure due to gravity first, because I want to show you all why we have to be careful. So the pressure due to gravity is going to be rho GH. We already said that. I'm just going to plug in the numbers. 1.05 times 10 to the 3 times positive 9.8 times 0.5. Now you're going to plug that in. And again, I told you all, one of the things with fluids that you got to be the most careful of is the units. Pressure of 5,145. What's my units? It's Pascal. If you say this is millimeters of mercury, you're insane. Not because you're actually insane, but like if you measure someone's blood pressure and it's 5,000, you did it bad. Like, it's not even like, oh, this is really bad. Like, it's just not a thing. Like, yeah. I don't even know what the max, I think like what's a bad blood pressure? Like 160, 180? Yeah, 5,000, like that's stupid. It's stupid large. I'm not going to give you a problem that is, the answer is 5,000 millimeters of, that's like a stupid, ridiculously large pressure. So, why am I making this point? You all got to convert this. If you want to add it to 120, don't add pascals and millimeters of mercury because they're not the same thing. So, this is going to be 5,145 divided by 133. 1 millimeter of mercury is 133. So, that's going to give us an answer that's much more reasonable. 38.68 millimeters of Hg. And then I need a new slide. Boop. And so I think this problem's kind of easier to see once you put in the numbers. The logic all starts to kind of like, if you're like, what the heck was he doing? Why was he doing all this? Once we start putting in the numbers, I think it makes it more clear. Look, making some blood pressure. How much blood pressure was the heart making? On the high end, it was 120. Great. Well, then there's literally fluid, because we measured 0.5 millimeters down, there's literally a bunch of fluid above it. The veins are filled with fluids. That fluid is also pushing down. You all know this. If you get on your head or something, a lot more blood kind of gets, moves to your head. Why? Because of gravity, like stuff There's a higher pressure as well. It's probably not good. Like, you feel the pressure in when you all do a handstand, you all feel that increased pressure in your head of all the blood. And it's not because there's literally more blood in your head. It's because all the fluid in the rest of your body is pushing down on the fluid in your head. So, that's kind of interesting. I think a lot of people do think that like, oh, there's a lot of blood. Like, kind of, sorta. There's probably a little bit more. All right, so you get this answer, 158.6 Hg for this one. And that was the high. And the low would be 80 plus this number. And this is an interesting one. To be honest, I don't know how accurate all this is. The body is kind of complicated. There's so many veins and arteries and things like that. But if you all have a way to measure blood pressure, do it for yourself. See how accurate these numbers are. Measure your blood pressure up near your heart. then measure it down to your leg and actually see how different it is. I imagine it's going to be different. It might not be this different. Notice that this problem does make a statement. Assume that there's no loss in pressure. It says it's fairly reasonable. So whatever. Okay, great. You get more pressure when you go down to fluid. That's the punchline. On to our next fun fact. Again, this PowerPoint slide is just like next fact, like it's a bunch of new facts, and each fact gets closed out by doing a problem. That's going to be the rhythm for this PowerPoint. And they kind of sort of build on each other. They all connect in various ways. So the next fun fact I need to teach you all, you can't squish a fluid. And you may be like, what do you mean you can't squish a fluid? You show me a picture of someone squishing a fluid. The purpose of this picture is to show you when you try to squish the fluid, it then tries to go somewhere else. It is impossible to make water molecules closer to each other and them to still be liquid water. Let me clarify that. You cannot, if you had water in a closed container, so let's imagine like a piston like this. So you had some piston and you had this thing filled with water. It would be impossible for you to push that piston down. It's one of the things about fluids. It's called incompressible, meaning not able to be compressed. And so what's really interesting about this is any change in pressure in the fluid happens everywhere in the fluid at the same time. That information travels like basically instantaneously. It's not technically instantaneous. There's a limit to how fast information can travel. It's the speed of light, yada, yada. This is probably at least the speed of sound, which for us is basically instantaneous in any container. This has all sorts of consequences, and we're going to look into one of them right now. But it's one of those things you just don't expect. You're always so used to like squishing you're like, I can squeeze a water bottle. Yes, that's because one, the water bottle can deform at the top, just like this little ball picture I'm showing you here. Other parts can deform. Also, there's a little bit of air. But if you got a sealed container, yeah, there's examples I can give you. I don't know if they're helpful. But yeah, you can't squish a fluid. Just can't do it. It's not possible. All right. With that in mind, that's an important idea. If you don't believe me, we can chat about it more. I can try to come up with more examples, but it is a thing. This is going to lead us into a consequence of this that's really cool. I got two pistons. These two pistons, underneath them share a fluid. So a piston, they can just go up and down. So on the left, I have a piston with a smaller area. On the right, I have a piston with a bigger area, and they share the same fluid. I push down on the first one, which causes some increase in pressure everywhere. These pistons can go up and down. They're both free to move, both free to kind of go up and down. If they weren't, nothing would happen. So we push down on this piston, it goes down, and my question to you is what's going to happen to the second piston? If I push down on this first piston with some force, will the second piston experience a large force downwards? So it's going to want to get pushed downwards. Will it experience a small force downwards? Will it want to go downwards? Will it experience a large force upwards? Or will it experience a small force upwards? And specifically, will it experience a larger force than I push it with, or a smaller force than I push it with? And the major point to understanding this, the pressure is the same in both. You need that new idea along with a previous equation that we learned to be able to answer this question. All right, we'll go like 10 more seconds. All right, in 5, 4, 3, 2, 1. All right, so how are we going to do this? We're going to use pressure equals force over area. Okay, so let's just make up numbers. Let's say I push this thing with 10 newtons. And because I'm lazy, let's make this area 1 meter squared. Nice numbers, right? Great. Let's calculate what pressure I get. So the pressure 1 equals 10 divided by 1. 10 pascals. That's a super tiny number, but who cares? All right. Let's look at pressure 2. That's going to equal force over area. But instead, I want the force. So I'm going to do P times A. Now, the area of this one's bigger. How much bigger? Let's just make it twice as big. That's nice and easy, right? It's a bigger number. Well, here's the thing, and this is the thing that's really important. The pressure is the same everywhere. So pressure 1 equals pressure 2, which means this equals 10 times 2, which equals 20 newtons. We have doubled our force. So this is something really cool. So it's going to experience a large force up. You push that one down, that one's going to go up. This is something I personally think is like, this is hydraulics. This is how hydraulics work. It is a way of multiplying force. I can push this thing, if this piston, this first one, it's easier to say it this way. If this second piston was 100 times larger in area, I get 100 times the force. This has so many applications that you all take advantage of. One of them is if you ever had to jack up your car, if you've ever seen like a car jack, that's how they work. It's hydraulics. You all are able to use a jack to lift the car. Now, it's not free energy because for every meter that you push this one down, it'll be, however much this goes up will be, if this is 100 times bigger, let's actually take this example. This is twice the area. For every 1 meter the small piston goes down, the other one will go up half a meter. So the work is still the same. Work equals force times distance. So the force is double, the distance is half. Great, whatever. Most of the time when you want a really large force, you don't need it over a big distance. Like jacking up a car, you're perfectly, well, you might not be very happy about it. But like when you're doing the jacking thing, sure, you might have to like jack it a bunch of times and keep doing it and doing it and doing it. But that's way better than lifting the car with your hands. Like, that's not even possible for most people. Maybe you can do it, I can't. Another example, this is your brakes. Your brakes, most brakes, I don't know if they've switched it to electronics at this point. When your foot hits the brakes, there's literally a line of fluid, a brake line is what it's called, with brake fluid in it, that goes from your brakes to the brake pads. When you push the brakes, it literally compresses the fluid, which in turn pushes the brake pads. The brake pads have a much bigger area than the one on your brake pedal, and it multiplies the force stopping your wheels. If you've never thought about this, stopping your wheels is not easy. I mean, could you do it? You couldn't just stick out your foot and like slow down your tires if they were going 60 miles per hour. But by pushing on the pedal of that, you can make your wheels come to a stop almost instantaneously. How do you do it? You multiply the force with the hydraulic line. Now, something really, really interesting about that is this only works if it's all fluid in your brake lines. If you ever change your brakes, one of the things you have to be so careful of is that there's no air bubbles in your brake line. If there's air bubbles in your brake line, what's going to happen when you push your brakes is those air bubbles are going to compress and your pressure won't increase. So what's going to happen is you can't compress a liquid, but you can compress a gas. So you'll hit the brakes, Sure, all the air bubbles will get smaller, but your brakes won't actually activate. So you have to do something called bleeding the brake line, which is basically where you get all the air bubbles out of it. You run fluid through until you make sure all the air is out of it. It's the thing you got to be the most careful about. It's really easy to test, though. Just before you drive, you just make sure your brakes work. But yeah, other examples of this is if you have ever seen like any construction equipment ever, the forces involved in construction are huge. So an excavator is something you probably are very familiar with, but probably haven't thought about much. These little things on it are pistons that multiply the force by they apply some pressure in a line, and then they have a big area in here. And the bigger these cylinders, the more force they can generate. You might never have thought about like how strong these things are, but if you've ever been near one of these buckets, it's like a meter by like a meter. And every scoop they're scooping up is a meter by meter of dirt. Have you thought about how much effort that would be to scoop that? Like in one scoop, they could scoop the amount of dirt that would take you like an hour. That's like a lot of force required. That's a lot of weight. Like that's each of these scoops, I don't know. I wouldn't be surprised if it was between 1,000 and 2,000 pounds of dirt that it picks up in a single scoop. That requires a lot of force. How do you get that force? Hydraulics. They don't move quickly. You're not like lightning fast, but it's quick enough. It's way quicker than anyone else is going to do it. These things move slowly because you get a force multiplication, but it's over like a long period of time kind of thing. So yeah, every construction equipment, all of them, it's hydraulics out the wazoo. And it's this simple equation right here. It's called Pascal's principle. The force over the area of one piston equals the force over the area of the other. And you can get how much the force gets multiplied. That's what we just did. Pressure equals force over area. If the pressures are the same, you set them equal to each other. Done. And you do some math. Bigger the area, larger the force. Pressure equals force over area. That's just the definition. So, yeah, I find this super, super interesting. Again, so many applications of this where you want to get a really strong force. It's with hydraulics. If you've ever watched the hydraulic press channel, how do they generate such strong forces? Fluids. And it's literally just this. Like, that's it. If you apply some pressure to some area, you can get some force. That's all you have to do. And now something that is important here, this just says if there's an increase in pressure, everywhere gets increased the same amount. It doesn't mean the pressure in a fluid is the same at every spot. And hopefully that's going to be really obvious when we just remind ourselves that in a tank of water, the pressure at the bottom is bigger than the pressure here because we just talked about there's a bunch of fluid above you, it's higher. So this does not say the pressure in a fluid is the same everywhere. It says the pressure increase at some point will increase the pressure everywhere else. If a pressure increases by 5, everywhere increases by 5. If the pressure increases by 10, everywhere increases by 10. So, in this picture, they were the same height, which is why they were the exact same pressures. That was for convenience. All right, and to close this one out, we do a problem with a syringe, which is basically a piston. So, I don't know why they call it specialized hydraulic syringe. That sounds really fancy. It's just a syringe. So you got your syringe. And inside your syringe, you got some plunger. That's your piston 1. Where's your piston 2? There's not so much a piston, so much as just like a small opening there. But pretend like there is a thing. Basically, we're just looking at how the forces compare. So this one I'll kind of breeze through because it's pretty straightforward. Area 1 is going to be 20 centimeters squared, which we're going to go ahead and convert to 0.002 meters squared. Area 2 is going to be 0.5 centimeters squared, 0.00005. Force 1 equals 60 newtons. We're solving for force 2. Pressures, same, all that good stuff. F1 over A1 equals F2 over A2. So F2 is going to equal F1 over A1 times A2. And you just plug in this stuff. It's fairly straightforward. Now, technically, we didn't need to convert from centimeters to meters in this problem. Because we're doing area divided by area, the units cancel, and it doesn't matter. But rule of thumb, if you don't know when you don't need to convert, just always convert. You won't make a mistake if you always convert. If you try to guess when you can and when you can't, that's when you'll make a mistake. So that's why I went ahead and converted. It's the safer option. It didn't take that much time. So F2 is going to equal 60 divided by 0.002 times my 0.00005. All right. And we get a force that's 1.5 newtons. If you do the math, 0.5 over 20 is 1 over 40. And 1.5 is 1/40th of 60. If you take 60 and divide it by 40, you get 1.5. It's the ratio of the areas. So they're pretty quick to calculate if you know what you're doing. Otherwise, you just go through the motions and figure out that. All right. There's one last idea I would like to plant in your head before you leave today. So we're going to we'll do this clicker. So that's great. Another thing we talked about, hydraulics. There's one last thing I want to try to plant in your head. So we're going to do this question, and then I'm going to show you a slide, and then we'll continue talking about it next class. But I want you all to see it so that your brain can at least be like processing it in the background, because it's probably one of the conceptually takes a bit to wrap around, even though the principle itself is really simple. The principle I'm about to teach you was discovered in 400 BC. It's like one of the first things that were discovered, which is kind of cool. So yeah, I fill a water balloon with water, and I put it underwater. Which of the following is the correct free body diagram for the balloon underwater if it's not moving? That's very important. Use the knowledge at your previous knowledge to answer this. Draw the free body diagram. Keep in mind it's not moving. Keep in mind we're on planet Earth. All right, we'll go 10 more seconds. All right, in 5, 4, 3, 2, 1. All right, great. I got my water balloon. It's on Earth. What force is there?
Gravity.
Great. Is my water balloon plummeting downwards due to gravity? No. There must be something canceling it. If it's not moving, something must be canceling it, equal and opposite. Now, I haven't taught you what that force is, which is why none of these are labeled. But you've probably heard it. It's the buoyant force. Now, what's really cool about this buoyant force is we can actually derive it from this expression. If it's not moving, how do those two compare? How does the buoyant force compare to the force of gravity?
Equal.
And in this problem, it's mostly water. So, fun fact, the buoyant force is equal to the mass of the water times the gravity. Boom, that's Archimedes' principle. The buoyant force is equal to the mass of the fluid that's displaced times gravity. The logic being, and this is the thing I want you to kind of ruminate on, if the object wasn't there, there'd be a bunch of water there. What's holding up that water? The buoyant force. That water is being held up. This sounds like a really weird idea. But there is water here. It's not falling. Why isn't it falling? Because this water experiences a buoyant force upward. And it's the exact same force as if you put an object there. And it's just equal to the mass of the fluid times gravity. Archimedes discovered it 400 BC. That's cool. Any object, this is how much water pushes up on it. You just figure out how much mass of water is displaced and multiply it by G. It's really simple. Anywho, we'll do a problem with an air mattress next time.